Okay, we are at the top of the hour. Good afternoon, and welcome to our next installment of the Safer Sim webinar series. My name is Jacob Hayden, and I'm the program coordinator for Safer Sim at the University of Iowa. And Safer Sim is a Tier 1 university transportation center with the research priority of promoting safety. And our webinar series features the research projects from our center. Thanks for joining us today. We will have time at the end of the presentation for questions and discussion, and attendees can use their microphone or the chat box to participate. Feel free to use the chat box at any time throughout the presentation as well. We will address those questions and comments at the end during that Q&A session. Um, with that, this webinar is being recorded and we will be sharing it afterwards as well. And our webinar today features a research project from the University of Central Florida. I'm pleased to welcome our presenter, Fatima Afifah.
Thank you, Jacob, for giving me the floor. Um, I'm Fatima, and I'm doing my PhD in University of Central Florida. Today, I'm here to present the Safer Sim project on vehicle to infrastructure placement and safety implications of connected and automated vehicles in an interconnected network. This project is a joint work with my PhD supervisor, Dr. Zaumia Guo. He's an assistant professor in University of Central Florida. So we will first start with the background and motivation in this presentation. And then we will talk about the research questions that we are interested in for this project. And we will talk about the methodology to address those research questions. Followed by that, we will present the results that will illustrate the methodology. And finally, we will summarize the project in the discussion. Every year, thousands of lives are lost on the roads nationwide. And if you look at the first figure, it can be seen that the number of road fatalities is pretty high in each year. According to National Safety Council, there were 30,000 fatal crashes in 2019, resulting in a total of nearly 33,000 deaths that year. These are some facts about road fatalities in recent years. On the other hand, in recent years, there has been a rapid advancement in the technologies for CAVs and V2I devices. These two facts might seem irrelevant at first look, but the next slide will clarify any confusion. So in this slide, we first talk about two known facts, and then we talk about the motivation. So the first fact is vehicle to infrastructure devices generate a lot of real-time information. And using those information, CAVs can make adaptive route changing decisions. The second fact is transportation system is an interconnected network. So therefore, any local route change or local traffic events has an impact on network level mobility and safety. So the motivation of this project is to leverage the CAV and V2I technologies to improve network safety. The research question we are interested in for this project is more information always better for network safety? Another question is, what is the impact of spatial information sharing on network level safety? In other words, what is the impact of information sharing location on network level safety? We conduct a rigorous literature review, and we divided into two parts. So the first part talks about CVs in improving local safety. In this literatures, CVs is used to improve intersection safety, signalized intersection, or roundabout safety. They do not specifically talk about any network level safety. In their work, they use microsimulation technique and surrogate safety measures for safety evaluation. And the second part we discuss is about CVs in network safety. We found a literature that uses V2V and V2I V2I devices to investigate network mobility and safety for CVs. They assume the fixed information for their work. They used microsimulation techniques for safety evaluation. We know that the microsimulation and their calibration in network level is difficult to achieve. The other literature talked about this used statistical models for network level safety. They are not able to analyze the impact of information sharing on network level safety. Therefore, we want to make an analytic model that would represent the network level safety. The research gap over here are as follows. Research on safety at network level safety is still quite limited. Um, After conducting a rigorous literature review, we found out that no study has been conducted for network modeling considering in-route information. And also, information sharing strategies and locations are considered as exogenous or are not considered at all. This slide presents the methodological overview of our work. We divided into three sections: network modeling, parametric estimation, and network safety analysis. They don't have any chronological order. We just represented it for better understanding. So in network modeling, we first make a transportation network for CAVs that takes in information from V2I devices, and that it generates traffic flow that can be used in parametric estimation. In parametric estimation, we evaluate the link performance function and collision risk. For both real data and microsimulation, we find the link performance function, which is the travel time, and then we use it on the network model, the transportation network model. If we have collision risk data, real data, then we can use directly to find the collision risk over here. And for microsimulation, since no collision data is available, we use surrogate safety measures to find the collision risk. Once we find the collision risk, we evaluate the network level collision risk in network safety analysis, and then we pass the risk information back to V2I devices. This slide presents the mathematical formulation of two-stage adaptive stochastic user equilibrium. So this is an optimization problem. The first equation represents the objective of the problem, and the rest of it the constraints of the problem. So in the first problem, in the objective objective function, we want to minimize the travel time for each link. And if we notice, we can see like 1B and 1C is flow conservation constraint. If we carefully look at this first three equation, we will see that these are the classical user equilibrium equations. We integrate that with the fourth equation, which is the non-anticipativity constraint. This non-anticipativity constraint is very important as we introduce the information on this equation. Also, non-anticipativity constraint ensures that if no information is shared in a link, the flow on that link would not depend on any scenario change. We illustrate the whole idea using this toy model. So we have this toy model where this link 1, 2, 1, 4, 2, 3, and 4, 3. The travel time, the link cost depends on the flow of those links. This is different for link 2 to 4. In link 2 to 4, the travel cost depends on this it can differ based on this parameters. So for example, in first scenarios, the travel time in link 2 to 4 is 5 minutes higher, and in the second scenario, the travel time is 5 minutes lower than usual time. We divide it into three paths. So path one contains 1, 2, 3, and path 3 is 1, 2, 4, 3, and path 3 is 1, 4, 3. There are two possible hyperpath or bundle path in the first stage. So hyperpath is a way of dividing all paths depending on whether they receive information or not. So there is two stages. The one is before information. So this node 1 can be represented as the first stage, and the second one is after receiving information. So we see that before, in the first stage, we have two paths, and only two of those paths can receive information. So we bundle it in one path, and then we use the rest to define the rest hyperpath. We provide a definition for the two-stage adaptive stochastic user equilibrium, which is an extension of a classical user equilibrium. So the expected travel time on all paths used in the first stage are equal and less than and any unused path. So we're talking about the first stage right over here. And on the second one, the expected travel time on the all paths in the second stage are equal and less than any unused path. So we're talking about the second stage right over here. Using this definition, we manually calculate the path flows for both scenarios. And we can see that in the first scenario, when the travel time in link 2 to 4 is higher, all traffic will use this route P1 instead of using P2. And in second one, we can see when the travel time is lower, the traffic will use P2 rather than using P1. After finding the path flows, we find out the travel cost for both scenarios. And then we find the expected travel cost. And we can see that both of them are equal, which validates the definition we have. In this slide, we talk about the parametric estimation. So we we evaluate two parameters. The first one is link performance function, and the other one is collision risk. For link performance function, we used BPR function as shown in equation 2. As we can see, like the terms T naught, alpha, flow, capacity, beta, they depends on scenarios. The evaluation of collision risk depends on whether we have information about the accidents or not. So if in collision risk, if real collision data is not available, we use surrogate safety measures. In this case, we use TTC or time to collision. Once we know the time to collision, we see two cases. If the TTC threshold is greater than TCN, meaning the end step, we're talking about step is as this is the we're talking about the microsimulation. So when this case happens, the difference of the terms gives us the collision risk for end state. Otherwise, it will be 0. Once we find the collision risk, we can use it on equation 5. We can use the flow from the network model, and then we can find out all the coefficients for equation 5. When real collision data is available, we use this equation 6, which is a decision-based model, decision choice-based model. We used real accidents information over here, and we used the flow from the transportation network and find out the V0 and V1, the constant, the coefficient for equation 6. So once we find the collision risk for link, as we have shown in the previous slide, we can use it to find the collision risk of the network. So the collision risk of the network is expressed as the total risk experienced by all vehicles in the network. We multiply the vehicle flow for each link with the collision risk for link, and we sum it up for all links. Once we do that, we find the collision risk for each of the network of each scenarios. Once we find the collision risk of the network for each scenarios, we find the expectation of all those scenarios, and we find the collision risk of the whole network. These are some preliminary results that we found, and we used two examples for it. In the first example, we use a 4-node test network using a Sumo platform. Each link is one way and 1 mile in length, and the speed of each link is 30 miles per hour. We have 3 paths as before, so P1, P2, and P3. In this slide, we talk about the information sharing strategies. So, for example, say like an accident or an incident takes place in 2-4. We can share the information in 3 ways. So in first case, we do not share information at all. In the second stage, we share information in node 1. And in the third case, we share information at node 2. After we define the sharing information strategies, we can find out the link flow for all stages. And as you can see, we define it in normal scenario and incident scenario. To show the link flow, we use the heat maps. The normal scenario is when there is no incident occurring, and the incident scenario is when an incident takes place. Um, if we take a closer look, we can see that in no sharing information case, for both cases, the link flow is same. This is because of the non-anticipativity constraint. That constraint says like if no information is shared, all the links would have the same flow despite of the scenario change. The second thing we want to notice is this two case, the first case and the third case. We can see that a lot of traffic takes link 1 to 2. This is because when information is shared at node 2, a lot of vehicles travels to link 1 to 2 to receive information and then go to their destination. Once they do that, there will be lesser vehicle in link 1 to 4, as can be seen from this the two scenario comparison. We also see that when information is shared at node 1, a lot of vehicle in normal case would use link 1, 2, and 4, 3, as shown in this figure. This is because a lot of people will use the P2 path to go to the destination. This will change when the scenario changes, when an incident takes place, as can be seen in the figure. For the third and final case, we see that if the link flow for both cases, the link flow for link 1, 2, and 1, 4 in both cases are same. This is because of, again, the non-anticipativity constraint. When information is shared at node 1, node 2, link 1, 2, and 1, 4 would not receive any information. Therefore, changing the scenario would not change the link flow. We generated a collision risk analysis over here, and we see that when information is not shared, the network would be riskiest. And when information is shared at node 1, it will be more safe for people. And even when information information is shared at node 2, it will be safer than not sharing any information. This is because when people have the information, they have the choice to reroute. For the second example, we use this Orlando network. The network covers an area of 78.87 miles square. We have 3 nodes that are darkened over here, node 3, node 11, and node 13, which represents the traffic for Disney World, Universal Studio, and Orlando Airport, respectively. We also collect traffic data from Regional Integrated Transportation Information System. We divided into 3 cases to analyze this network. The first case, origin would be the node 17, and this node 17, which is the Orlando International Airport, and destination would be Disney World, node 3. And the incident will take place near the origin. So when that happens, we see like we compare 2 cases, normal case and incident case as before. When information is shared at node 17, we see that a lot of traffic use route 6 to travel to the destination. And when an incident takes place and information is shared at node 17, we see that they avoid the same amount of traffic, avoid the link 14 to 17 and takes a longer route 26 to reach to this destination. We find the collision risk of the network in this model with the color bar. This is defined as if information is shared at each node, how would it impact the collision risk for the whole network? So we see that when information is shared at node 17, people would have the highest chance to reroute, and it will be safest. For the second case, we flip the origin and destination. So this would be the origin, node 3, and node 17 would be the destination. and we keep the same link for incident. So this case is significant because we try to see what will happen to the network safety when the incident is further away from origin. It was not like that before. So when we do that, we see that there will be a significant amount of traffic that travels to the information node to receive information. By that, what I mean is, say this information is shared in node 13. In normal case, they would use route 26 to reach to destination. And in incident case, they will take that node and then they will reroute to route 25 to reach to the destination. So a significant amount of traffic did receive information over here and then reroute. We do the same analysis as before for to find the collision risk of the network, and then we see that node 13 is the safest for this case, and node 4 is the one that will have more that will be more riskful for the travelers to travel to the destination. Finally, we have the 6 OD pair case. So by 6 OD pair, we mean like node 3, node 11, node 7. All three nodes are used both for origin and destination. In this example, we take two links for incidents. So it would be 3, 5 and 14 to 17. When we do that, we see that it would be safest when we share the information at node 6. This is because node 6 is relevantly is center in a center place than any other nodes for all 6 OD pairs. When information is shared at node 1, 2, 4, 7, 8, 16, it will make the network risky. And one thing to notice is that if more information is shared, it's not always good that for the network. For example, if information is shared at node 8, a lot of traffic will reroute to this node to receive information. And the more you reroute, the more you are at risk in the network. So to summarize, we can see that more information shared may not always be the better case. Information sharing will influence the rerouting decisions. Information sharing at the different locations could dramatically impact the network safety. The specific impact of the information sharing location will depend on the specific setting. The proposed methodology that we have is a general case, and it can be expected for any network. We can do a few more numerical experiments to solidify our methodological approach. We have not considered any heterogeneous information, so we only considered one universal information for the whole network. And we did not distinguish any, we did not distinguish what information to provide or which group to provide in our examples. And we only consider mobility information for route decisions in our examples, and we did not consider reliability, safety, and sustainability, which can be considered in future studies. These are the references that we used for this slide. If you have any question, you can ask us or email us. Thank you so much.
Thanks, Fatima. We did have a question come in during the presentation. How do you calculate the expectation of the network collision risk? Any probability consideration?
We use this function to find the collision risk for the expected. So yes, there is a probability. So since we have two scenarios for all the examples, the scenarios for the probability will be half.
Thank you. Okay, I'll leave the chat open for a little bit longer. While we're waiting for others to come in, I'll thank everyone for joining this presentation. It will be available online on our YouTube channel and the website in the next couple of days, and we will share that out with everyone that registered. So feel free to share that with any colleagues that may be interested once you receive that. And then our next webinar will be later in July, and it will feature another project from the University of Central Florida. So we're excited to hear from them again. We will send more registration information about that in the coming weeks. And with that, I'm not seeing any other questions. So as Fatima mentioned, she did put the email addresses on there to the last slide. Fatima, I'll let you go to that slide one more time. So if you do have any last questions or comments or want to reach out to them directly, you can see their email addresses there. We will also include their email addresses when we're sharing that online webinar once it's posted. So I think with that, that's all we have. Thank you again for your presentation, Fatima, and thanks everyone for joining.
Thank you.